Somewhere over the Atlantic at 37,000 feet, the cabin jolts. Drinks slide off tray tables. Overhead bins rattle. And from the window seat, you watch hundreds of tons of aircraft hanging from two narrow structures that are visibly bending under stress. Every instinct tells you something is about to give. But here is what the engineering says. Those wings can flex dramatically during testing and still remain below the point where engineers expect failure. During certification, they are pushed to loads the aircraft will almost certainly never see in service. And they hold. The movement you notice from your seat is not a warning sign. It is a structure doing precisely what it was built to do. They do not survive because turbulence is imaginary, because wings are rigid, or because a few bolts somehow hold everything together. The real answer runs deeper, through decades of material science, catastrophic failure analysis, and testing standards forged from lessons that once cost lives. To understand why wings do not snap, first understand that bending and breaking are not the same event, and that difference changes everything about what you are actually witnessing from that window. Inside the cabin, the human inner ear is highly sensitive to vertical acceleration. When an aircraft strikes an updraft, passengers feel a sudden acceleration, a sharp change in speed that triggers an immediate threat response. But the wing itself experiences this simply as a shift in aerodynamic load. To the human eye, watching a wingtip sweep upward suggests structural failure. Yet, structural physics dictates a different reality. A completely rigid wing would act like a stiff branch, concentrating stress at the root until it snapped. By allowing the structure to bend, engineers distribute these intense aerodynamic forces along the entire span, safely absorbing the energy of the gust. Passenger discomfort and structural threat belong to entirely different categories. The rattling of overhead bins is an uncomfortable sensory experience, but it is not a measure of structural distress. Ultimately, what looks alarming from the cabin is often a structure working exactly as designed, using controlled elastic deformation to protect the airframe from sudden changes in force. If a wing were completely rigid, every strike of turbulent air would concentrate massive forces at a few specific points, leaving those areas highly vulnerable to local overload. Instead, an aircraft wing is designed to undergo elastic deformation, bending within a precisely calculated range and returning to its original shape once the load passes. This bending action distributes the changing aerodynamic forces along the entire span of the wing, preventing any single point from bearing the brunt of the impact. During flight, these forces fluctuate constantly. Lift, vertical gusts, sudden maneuvers, the weight of fuel inside the wings, and the heavy engines hanging beneath the structure all create a dynamic, shifting load environment. Wingtip movement does not mean the wing root is separating. Rather, it is the visible result of a highly coordinated internal structure at work. It shows that the wing is actively dissipating energy. Rather than functioning like a simple shelf hung onto the side of the aircraft, the wing is deeply integrated with the fuselage. At its core is a complex load-sharing network of internal components. The outer skins and the longitudinal stringers stiffen the surface against buckling under intense aerodynamic pressure. Inside, transverse ribs maintain the wing's aerodynamic profile and channel forces into the longitudinal spars, the heavy structural beams running the entire length of the span. Together, these elements form a rigid, closed-section structural core known as the wing box. This structure transfers the intense bending and twisting forces directly into the center wing box, which is built into the fuselage itself. Because these components work as a unified system, bending distributes the force through multiple structural members rather than trapping it at a single point. But flexibility only explains how the wing responds. How do engineers know how much force it can survive? Engineers quantify the forces acting on an aircraft using the load factor, measured in units of gravitational acceleration, or G. In steady, unaccelerated level flight, the lift generated by the wings exactly equals the weight of the aircraft, representing a load factor of 1g. When an aircraft encounters atmospheric gusts, convective updrafts, or initiates a pilot-commanded maneuver, this balance shifts, briefly increasing or decreasing the load factor relative to normal flight. To ensure the airframe can withstand these fluctuations, Certification standards establish strict, measurable load thresholds. The first is the normal operating load, which covers typical stresses of daily flights. Next is the limit load, defined by the Federal Aviation Administration and the European Union Aviation Safety Agency, as the absolute maximum force the aircraft is expected to encounter over its entire operational lifetime. Under limit load conditions, the wing must support these forces without suffering any permanent, harmful deformation. It must bend and then return perfectly to its original shape once the load is removed. Beyond the limit load lies the ultimate load. Under transport category rules, engineers apply a safety factor, multiplying the limit load by 1.5. The wing must support this ultimate load, 150% of the highest expected in service force, for at least 3 seconds without structural failure. This safety factor provides an essential margin for material variability, environmental degradation, and load path redistribution. Proving compliance does not require manufacturers to take every production airframe to structural destruction. Instead, type certification relies on a comprehensive matrix of evidence. Engineers couple highly detailed computer simulations and finite element models with physical fatigue rigs, localized component testing, and full-scale static tests. During static trials, massive hydraulic systems apply distributed force across the entire wingspan to monitor stress, joints, skin, and spars. Verified certification footage of the Boeing 787, Airbus A350, and Airbus A380 demonstrates these recreated loads, showing wings flexing dramatically without rupture, but to validate structural calculations. The wing is not tested only for the flight everyone expects. It is tested for the loads engineers must prove it can survive. But turbulence is unpredictable. How can testing account for air that strikes without warning? In the atmosphere, turbulence is not a void or a literal pocket of empty space. It is a region of rapidly changing airflow. When an aircraft flies through these shifting currents, vertical and horizontal gusts temporarily alter the angle of attack, rapidly increasing or decreasing the local lift produced by the wings. This abrupt change in lift produces vertical acceleration. The human body is highly sensitive to sudden upward or downward motion, translating even minor accelerations into a strong sensation of danger. Yet this visceral physical response does not correspond to a structural crisis. While passengers feel the sharp jolts of a cabin rattling, the wing experiences these inputs as transient, fluctuating aerodynamic loads well within its elastic design limits. Pilots and aircraft systems actively manage these environmental loads. Flight crews monitor convective weather systems using onboard radar, pilot reports, and meteorological forecasts, allowing them to adjust routes or climb to calmer altitudes. When entering turbulent air, pilots reduce speed to a specific turbulence penetration velocity. This target speed, specific to each aircraft type and weight, ensures the wing will stall safely before aerodynamic forces can impose a structural limit load. On modern fly-by-wire aircraft, automated systems assist the crew. High-frequency sensors detect atmospheric disturbances instantly, prompting flight computers to command subtle, rapid adjustments of the spoilers, elevators, and ailerons. While these active gust load alleviation features do not eliminate turbulence entirely, they redistribute the aerodynamic forces across the wingspan, smoothing the ride and reducing structural fatigue. The aircraft does not need to defeat the atmosphere. It needs to keep the resulting loads inside a structure designed to absorb them. Subscribe to follow along as we break down the engineering of modern flight. Building a wing is not simply a matter of making it as thick and solid as possible. Adding structural mass solves the immediate problem of strength, but it introduces heavy penalties. Every extra kilogram of metal or composite increases fuel consumption, drives up carbon emissions, and raises lifetime operating costs for airlines. Because of this, engineering margins are deliberate and highly refined, balancing structural safety with economic reality. A commercial airliner wing is built to survive decades of continuous service. It does not only face rare extreme gusts, it must endure tens of thousands of takeoff and landing cycles, flight maneuvers, and smaller repetitive atmospheric loads. Over time, these cyclic stresses can cause microscopic changes in the material. To prevent these forces from causing structural failure, engineers rely on redundant load paths. If one element experiences a crack or localized damage, the internal structure redistributes the weight to adjacent spars and stringers. This philosophy is known as damage tie tolerance. By designing the structure to remain strong even with minor flaws, maintenance crews can detect and repair issues during scheduled inspection intervals, which are supported by built-in corrosion protection from the day the aircraft is manufactured. The fundamental importance of designing for long-term durability was illustrated by the tragic structural failures of the de Havilland Comet in the 1950s. While those accidents involved cabin pressurization cycles rather than wing fatigue from turbulence, they taught the aviation industry a permanent lesson. A structure that is perfectly strong enough to handle a single high load can still be defeated over time by repeated, smaller stresses. The Comet disasters reoriented engineering philosophies toward tracking fatigue and ensuring that structures are designed to tolerate damage over thousands of flights. Modern wings are the direct result of this evolution. They are built so that the elastic bending observed during a turbulent flight does not compromise the underlying molecular structure of the spar or skin over its 30-year lifespan. The wing must bend today without becoming weaker tomorrow. Modern aerospace engineering relies on a dense loop of design validation that goes far beyond historic methodologies. High-fidelity computational models, including finite element analysis, allow engineers to simulate thousands of load cases before physical construction even begins. High-speed wind tunnel testing and full-scale fatigue rigs validate these digital predictions, ensuring that the physical airframe behaves exactly as predicted. Today, sensor data from active fleets feeds directly back into engineering databases, providing real-world validation of structural behavior. The introduction of carbon fiber reinforced polymers redefines wing construction. These composite materials, used extensively on aircraft like the Boeing 787 and Airbus A350, offer exceptional strength-to-weight performance and high resistance to fatigue. Yet composites are not indestructible, and they behave differently than aluminum. Because damage in composite structures can occur internally without visible surface deformation. Maintenance technicians use advanced non-destructive testing techniques, such as ultrasonic scans, to inspect the inner layers. In the air, digital flight control systems continuously monitor aerodynamic conditions. By automatically adjusting control surfaces like spoilers and ailerons, modern fly-by-wire systems reduce the peak bending moments experienced by the wing during turbulence. These advancements do not make aircraft immune to severe atmospheric forces, but they ensure that the safety margins established during design are systematically preserved throughout decades of operational service. Subscribe to follow our series on aviation engineering. While a wing is engineered to flex, aircraft structures are not invincible. When turbulence causes harm, the primary danger is almost never a structural failure of the wing. Instead, it is the immediate risk of unsecured items and unrestrained occupants being thrown about the cabin. The Federal Aviation Administration reports that about 58 people are injured by turbulence each year in the United States, and nearly all seriously injured passengers were not wearing seatbelts. Of the serious passenger injuries studied by investigators over a 10-year period, only one occurred while the passenger was belted. Extreme forces can damage cabin interiors or require intensive post-flight inspections. But true structural failure requires conditions far exceeding ordinary clear air turbulence. Wings fail only under extreme overload, collisions, explosions, maintenance errors, design flaws, or severe undetected damage. For example, when Aloha Airlines Flight 243 suffered a catastrophic structural failure on April 28, 1988, it was not due to turbulence. The Boeing 737-200 had logged over 89,000 flight cycles, leading to widespread metal fatigue and corrosion in the fuselage skin splices. This pre-existing damage, combined with pressurization cycles, caused an in-flight decompression, distinguishing it entirely from a wing snapping in rough air. Protecting an airframe relies on keeping operational loads within limits. Certification does not make failure impossible. It makes expected operations, including turbulence, fall far inside the designed envelope. Subscribe to follow our series on aviation engineering. Future wing development avoids the impossible goal of building an indestructible structure. Instead, the focus centers on refining how engineers predict, monitor, and manage atmospheric forces. Meteorological models and satellite-based wind shear detection systems provide flight crews with increasingly accurate, real-time forecasts, allowing them to navigate around convective activity and severe clear air disturbances. When turbulent air is unavoidable, next-generation gust load alleviation systems make rapid, automated adjustments to control surfaces, smoothing out the ride and reducing the instantaneous load on the airframe. Alongside these active flight systems, the internal structural health of the wing itself is becoming transparent. Microscopic, embedded sensors can track internal stress levels in real time, while advanced algorithms compile the exact load history of every flight cycle. This continuous tracking improves how operators analyze long-term structural behavior, moving maintenance from fixed calendar intervals to real-time condition monitoring. The aircraft of tomorrow will not achieve safety by trying to overpower the atmosphere. Instead, they will rely on continuous prediction and precise monitoring to keep every flight safely within its design limits. Every day, thousands of flights rely on one truth: materials must yield to survive. Visible wing flex is not weakness, but a calculated defense against the atmosphere. As global flight paths face more frequent weather extremes, this silent elasticity remains our safest shield. Subscribe for more deep dives into aviation engineering.